We present control operators for interactive character animation. Control operators are a flexible and powerful way of describing the desired behavior of interactive character controllers, making it easy to build controllers that can perform multiple different skills using a variety of control methods. For example, here we show a flow matching-based interactive character controller, which can follow a user-given path in different styles. Be controlled using a gamepad. Go towards a target point with a given facing direction. Sit down. And get up. Jump to target. And dance, all using a single neural network. While neural network-based character controllers have made great progress in the last few years, specifying the behaviors is still somewhat difficult. Text conditioning is simple and intuitive to users, but it isn't an appropriate modality for interactive control in video games, where precision and reactiveness are important, and typing out commands is impractical. Existing interactive controllers therefore often require complex feature engineering and network designs to express and handle different control variables. The fundamental idea behind control operators is to break down the control problem into individual operators, which have both a semantic meaning to users and an associated neural network structure used to encode each control. Complex operators can be defined with flexibility by combining and composing basic operators. We implement control operators in Unreal Engine's Blueprint visual scripting language, allowing users to specify the types of control they want, how they are linked to gameplay variables, and the training animation data. We showcase control operators on two state-of-the-art character controller types: a float matching-based autoregressive generative controller, and a controller based on learned motion matching. At each frame, control operators convert the gameplay inputs into an encoded control vector. This encoding and the previously latent pose are then fed into a network, and then it transports a random noise sample into the next frame's latent pose. The encoded control can also be mapped directly to the next animation segment using learned motion matching. We now explain some of the different operators. The now operator is the most basic operator. It represents the empty control with our float matching model. This effectively produces a random walk of the training dataset. The next most simple form of conditioning is to take numerical property of the training data, such as root velocity, and condition the generation such that the generated animation has the same property. The AND operator conditions the generation according to two or more other controls, for example, desired velocity and desired facing direction. The array operator conditions on an array of controls of the same type. Here we show it used to condition on the future trajectory. The optional operator describes that a control may or may not be provided. For example, in this move to target setup, desired facing direction is sometimes given and sometimes not. The OR operator describes that one of the given set of controls will be provided at runtime. This can be used to train a single controller with multiple different modes of control. An inclusive OR operator can be defined to describe that any of the given subcontrols may or may not be provided. For example, here we condition on different combinations of desired velocity, facing direction, and lookat directions. By composing such controls together using the operators, we can build controllers which can perform multiple skills using a single network. We now show a few more results using our float matching model. Here we show some more different styles of locomotion, trained on the 100-style dataset. Here we show some uncontrolled dance generation trained on the Motorica dance dataset. Control operators allow for cross-task generalization. Here we train a controller capable of either following a user trajectory or move to a target. The network is able to stylize the move to target task, even when only the trajectory following task was trained on stylized data. This is because control operators can map controls from different tasks to the same encoding. Here we visualize the control encoding for both trajectory following and move to target. The network uses the same control encoding for left turns, right turns, and forward motion, when that control comes from target point or trajectory to follow. In conclusion, we presented control operators, a powerful and flexible way to design control mechanisms for interactive character controllers that makes it easy to build models with a diverse range of skills and control methods.